So good afternoon, and thank you for joining this webinar organized by the Physical Acoustics Special Interest Group of the UKAN Plus. My name is Shahram Tahezadeh, and I have the pleasure of introducing today's speaker, Dr. Rodolfo Venegas of University of Austral in Chile, and also head of Institute of Acoustics there in that university. Dr. Venegas obtained his PhD from Salford University in UK and was co-founder of Carbon Air, which is an offshoot of University of Salford, dealing with porous applications of porous material. So worked there. He's been research fellow in a number of places, including universities in France and Salford. And as I said, currently he's a senior lecturer, associate professor in Institute of Acoustics and University of Austral in Chile. The title of today's talk is Nano-to-macroscopic wave propagation in multiscale sorptive metamaterials. Before I hand the virtual microphone to our speaker, I'll just remind you that if you have any questions, we will have a time for questions at the end. So please allow the speaker to finish his presentation. Then you can ask questions either by raising your hand and speaking, or leaving a message in the question and answer. Okay, so without further ado, I welcome Dr. Venegas and ask him to start his presentation. Thank you.
Thank you very much, Sharon, for the introduction, and thank you for the opportunity to present our work in this webinar series. So the talk today, I'll talk about nano-to-macroscopic wave propagation in multiscale sorptive metamaterials. So it's basically the combination of two kinds of materials. One of them is multiscale materials, and the other one is metamaterials. So this works in collaboration with Claude Boutin, Olga Nova, Alan Sam, Benoit Kwan, and Jorge Arenas, as well as the associate and students of the group I have the pleasure and honor to lead. So I'll start talking a little bit first about the, where I work now, and then I'll go into some more technical content, starting from recalling what the acoustics of rigid frame porous materials is, and then I'll go into multiscale sorptive materials and the mixture of these type of materials with arrays of chemicals resonators, and therefore that's where the metamaterials part comes from. And finally, I'll speak about our ongoing work on molecular to macroscopic modeling of hierarchical porous medium. So the Institute of Acoustics is part of the University of Austral of Chile. We're based in Valdivia, which is in the south of Chile. This is in the entrance of Patagonia, the Chilean side of Patagonia. And this is a picture of our city. So it's surrounded by rivers and it's very green. And that greenery comes from a lot of rain, as it is. It's very similar in a way to England. And this is our institute. So we run an undergraduate engineering program in acoustics and a master program in acoustics. We are at present time about 11 academics with diverse research interests, including noise control, soundscapes, and environmental acoustics, acoustics of materials, and physical acoustics, among other subjects. I would invite you to visit this website for more information. So what we understand by conventional permeable materials is a way of denominating three or four classes of materials. One of them is a porous material, which can be thought as a solid matrix with fluid saturated holes, like this copper lotus sample. And another type of permeable materials is a granular or a fibrous materials, like this is a fibrous materials, and this is a granular material, so that we can understand those materials as assembly of solid inclusions surrounded by a fluid network, or a cellular material, which is a cluster of fluid saturated cells like a foam, like this one. So what we can see and that these material shares are that we can define a porosity, which is the fraction of air in the material. For an acoustic materials, it could be other fluid for other applications. And we can also define a characteristic length. So for example, in the case of this porous material, it could be the pore radius. In a fibrous material, the fiber radius, and in a cell, like the cell size. So provided that the wavelength is much longer than any of these characteristic sizes of the materials, and together with motionless frame and scale separation. Motionless frame meaning that we are only interested in this particular part of the talk, in the propagation of sound through the fluid part of these materials. Then we can model all of them as an equivalent fluid with an equivalent or effective compressibility and effective density or permeability. So to demonstrate that, we can use a method that is called the two-scale asymptotic method of homogenization, which the objective of this method is to derive an equivalent macroscopic model that encapsulates this local physics through effective parameters. We rely on the separation of scales, quantified through this epsilon parameter, which is the ratio between the local characteristic size and the macroscopic characteristic size. There are several steps in the method that allow us to derive this equivalent macroscopic model, starting from the local description or the equations that describe the physics at the local or pore scale. So we do a physical analysis, we introduce two spatial variables, we do the rescaling of the local equations, and then we propose some answers, identify local problems, and finally we derive the macroscopic equations that encapsulate this, as I said, the local physics through effective parameters. So I would recommend to check these two books on the subject. They're really good books and very useful ones too. And coming back to acoustics of single porosity rigid frame porous materials, here we have a diagram of the macroscopic scale, and if we make a zoom in, we get this representative elementary volume, or the microscopic scale, which is constituted by a solid frame in black here, some pores in white, and again, if we consider separation of scales with respect to, for example, the wavelength, which is related to this macroscopic scale through this expression, we can have that material, for example, a granular material with a grain size of about 1 millimeter, can be considered as can be modeled as an effective fluid because the wavelength, for example, for 100 Hz sound is much longer than this 1 millimeter grain size. So in terms of physics, what we get is we start from the linearized equation of conservation of momentum, mass, energy, and equation of state with boundary conditions of no slip and null temperature variation on this gamma, on these walls of this, for example, this grain. And after applying homogenization, we get this macroscopic description, which is composed by the macroscopic equation of conservation of mass and this fluid flow constitutive load, which is the dynamic Darcy's law. In terms of dissipation, we have two main mechanisms here that are responsible for the dissipation of sound energy, and one of them is gas viscosity and thermal exchanges. So in a conventional material, the gas viscosity effects are accounted for by the dynamic permeability K, and the thermal exchanges between the fluid and the solid frame by the effective compressibility. So if we, for example, consider, just for simplicity, it is not strictly necessary, but for simplicity, if we consider macroscopically isotropic materials, this dynamic permeability tensor becomes a scalar, and we can rewrite these two equations as a diffusion equation where D is the pressure diffusivity. And this calligraphic K is called the hydraulic conductivity. Is basically the permeability divided by the dynamic viscosity of the fluid. And this is a very useful equation because it will give us an idea of how the nanoporous material compares with a conventional porous material. So before that, let us recall some properties of the dynamic permeability. So if we scale it with its static value at low frequencies, it will tend to 1. And in this regime, the fluid flow is dominated by viscosity effects. As the frequency increases, we have a transition where the real part and the imaginary part have the same magnitude, and that happens at the Biot characteristic frequency or viscous characteristic frequency. The imaginary part itself, it shows us how strong the dissipation of energy is. So it will be maximum around this frequency. And then when we keep increasing the frequency, we will have that this parameter becomes mostly determined by the imaginary part and with dependence of 1 over omega. And in this regime, we will call that, we will say that the inertia is dominating the fluid flow in the material. Similarly, for the compressibility, we scale it by the isothermal value, which is the porosity over the equilibrium pressure. It will tend to 1. There is a transition region determined by this thermal characteristic frequency. And at high frequencies, we will say that the propagation of sound will be adiabatic and the compressibility will become real. And in its normalized version, it will tend to 1 over the adiabatic exponent or specific heat capacity ratio. So those are the properties of a conventional porous material. We will see that in nanoporous materials and in particular in multiscale nanoporous materials, these properties, in particular the compressibility, is largely affected by different physical phenomena and physical processes that are happening at different scales of these materials. So by a multiscale nanoporous materials, we understand that is a material that has a hierarchy of pores. So here there is a SEM and TEM images of hierarchically structured zeolite. So we have heterogeneities range with sizes ranging from nanometers up to micrometers, and then these materials are normally made as pellets or granular materials, and therefore we have an additional scale which is related to the size of these grains or the pellets. And on the right, we have aerogels, also a similar structure, very tiny pores. In this case, this is sort of a collection of colloid type of particles, which are in the order of, let's say, up to 10 nanometers. And then in between these colloid particles, we have some nanopores. And these materials are structured. And again, they can come in granular forms, or as we will see later in the presentation too. So those are the 2 examples. And another example of this type of materials is a granular activated carbon. Here we have some grains, and then if we make a zoom in, we will see these microscopic micrometric size pores, which are these holes here and there. And this seemingly solid part is actually made of a nanoporous domain. So we have nanopores in this part, as we see here, not the holes. So conceptually, we have 4 different scales in activated carbons. One of them is the macroscopic scale, it's the scale of the sample, which would be this scale. And then we have the scale of the grains, these ones here in the order of 1 millimeter. And here we have the scale of the micrometric pores. So these are pores in the order of 1 micrometer, like these ones, for example, that hole, those ones. And then we have pores in the order of 1 nanometer. So roughly we have a separation of scales. Well, one of characteristic size LM, for example, is 1,000 times bigger than the LM, and LP is 1,000 times bigger than LM. And so on. So we have a very large separation of scales, and what we will call high permeability contrast will determine the behavior of these type of materials. So we have periodic hierarchical materials saturated with a pure Newtonian fluid. There is a scale separation, as I mentioned previously. And in order to describe the properties of these type of materials, we will make successive use of 2-scale asymptotic method of monization. So we will start from here. We will upscale it up to this scale, the model, and then we will combine this upscale description with the Fourier-Stokes system formulated in this around these grains, and we will apply again homogenization to get the macroscopic description. So we will use the method twice. What characterizes these materials in terms of sound energy dissipation is that we have classical viscothermal dissipation of different scales, at the scale of the grains, at the scales of these macropores, and also we have pressure diffusion interacting in between this scale and that scale, and that's affected by sorption and rarefaction. Rarefaction happens in very small pores, and sorption mainly happens in nanopores. And also we have mass diffusion affected by sorption. I will explain in more detail what these diffusion processes are along the way. So first, let us talk about mass diffusion. So it's a flux of molecules from a region of higher concentration to one of lower concentration. Absorption is a word that we use to describe two different physical phenomena. One of them is absorption, which is the addition of fluid molecules onto a surface, which is represented here with black circles. And desorption is the inverse phenomenon. So, for example, if we increase the temperature, these molecules will be released off this surface and they will appear in this bulk of these small pores. And this is represented in circles, white circles. So in terms of modeling, we have a mass flux that has two contributions, one of them coming from absorbed molecules and the other ones for let's say, free molecules. The mass, and if we do a mass balance, we get this equation, and we need the relationship between the absorbed molecules and the free molecules, and we consider that through a local isotherm where H is a proportionality constant. So combining all of these equations, we get this diffusion equation where D is effective diffusion coefficient and H is an effective sorption equilibrium constant that depends on the volume fraction of the system available for the free molecules to diffuse through it. It depends on the nanoporosity of the material, and also two different diffusion coefficient. One of them is the bulk diffusion coefficient, and another one is the surface diffusion coefficient. So this is interesting because it helps us to compare a conventional nanoporous material with a conventional material with a nanoporous material. And if we write this equation in terms of pressure by assuming that the process is isothermal, we can identify this pressure diffusivity just like the ratio between the effective diffusion coefficient and this effective absorption coefficient, which works in pretty much the same way of a porosity, but an effective one that can take values larger than 1, and we will see the effect later. If we compare these two equations, they are formally the same, and we can define the pressure diffusivity in a conventional porous material as the ratio between the hydraulic conductivity and compressibility, and in a nanoporous material, the ratio between these two parameters. And the other expressions show the direct parallel between these two type of medium. So we formulate equations in the micropores, equation of conservation of momentum, mass, energy. And also we have already this diffusion equation governing the mass transport in this nanoporous domain as modeled as an effective fluid. And then we have equations of continuity of mass flux, continuity of pressure, and continuity of and temperature jump condition. And here we have two components. One of them comes from the rarefaction effects. So the velocity is proportional to this allowed a tangential degree of velocity. And then this is to do with the normal part of the component of the velocity component, which is associated with the mass flux. So, and this epsilon comes from the scaling, and in particular, these two epsilons account for the fact that rho n varies at the local scale, and the other epsilon comes from the fact that this mass flux is an order smaller than the mass flux generated by the acoustic waves propagating in these micro pores. So applying homogenization, we identify different problems. This is a Stokes problem with a slip boundary condition, an oscillatory heat conduction problem accounting for rarefaction effects through this temperature jump condition, and also a diffusion process, sorry, the mass diffusion problem with a force diffusion, force density on gamma, meaning that the pressure here is forcing this diffusion to happen in this domain. So these are three linear problems. The solutions can be written as operators acting on the forcing terms in terms of fluid flow with respect to the gradient of pressure, for heat conduction to pressure, and mass diffusion also with pressure. And this can be thought as an equation of state, where this term shows that the response of the media is not automatic, it's not instantaneous. There is like a lack of time, a characteristic relaxation time working here, meaning that this will represent another way of dissipating some energy. So then we identify from the equation of conservation of mass the macroscopic description. So we take the average of this equation, and then we identify the source term. And this is very important because normally this term is zero for conventional materials, but in this particular case, we have the effect of what's happening at a smaller scale coming from this term. And in particular, this term can be written as in this way. And then when it is we take the average, we use the divergence theorem, and then we can write this divergence of velocity in terms of rho n, and rho n is already known, which is given by this expression here, and we end up with a classic, like it looks like a classic macroscopic description with a mass balance equation and a dynamic Darcy's law, with the difference in blue where we have that Cn is the contribution of the nanopores domain compressibility, and F is a function that accounts for the interscale mass diffusion processes. So in particular, Cn is proportional to He. H is the absorption equilibrium constant, and F takes this classical form. So now that we have this macroscopic description for the first part of it, we use it and couple with the Fourier-Stokes system to upscale the problem a second time in order to get up to the macroscopic description. Sorry, macroscopic scale. So in a similar way, we formulate a continuity of pressure, temperature, and also mass flux. And we upscale this set of equations to get a macroscopic description of the same type, but now we have that compressibility has a contribution coming from the pores and from then, let's say, what it is in black here, which accounts for the micropores and the nanopores that are inside this domain. And in this particular case, F accounts for pressure diffusion. So I'll skip this because all these are like explicit expressions of these effective parameters. And I'll go into the properties of this. So if we consider a single porosity material, this is what we would get when we normalize it. And it is a very small compressibility at low frequencies, and at high frequencies is very small too. So the difference between the low frequency and high frequency value will determine how large the magnitude of the imaginary part is. So if we have that this value is equal to the one at high frequency, it means that we won't have any dissipation of sound energy. This is not the case when we consider triple porosity material with absorption, where at low frequencies, we have a very large value of normalized compressibility, and at high frequencies, it tends to the value of a conventional single porosity materials where no absorption is happening. And the other cases are triple or double porosity material, but without absorption. So absorption, and in particular, this parameter determines this behavior. So in terms of the imaginary part where of the compressibility, which accounts for all these physical phenomena that are happening, in particular heat transfer in the pores, heat transfer in the micropores, that's the pressure diffusion, mass diffusion. And also this HE, this absorption equilibrium constant, is playing a significant role. So what happens is that because absorption in particular, the transport processes are slowed down, meaning that the characteristic frequency go down in values. And also because of this absorption, we have that the magnitude of the imaginary part is much larger than in the case of triple, double porosity, single porosity with absorption. So those are the two effects that can happen, and these are very convenient effects because it can lead to a very slow normalized speed of sound, as it is shown here, and a very large attenuation coefficient at low frequencies, as it is shown here. So in circles, these are measurements, and in black lines are the predictions of our model. So in terms of some absorption, let's imagine that we have a granular material with solid grains. This is what we would get as some absorption. And then if we consider triple porosity material with absorption, we get this black line. So it's a significant jump in the some absorption coefficient from, let's say, smaller than 0.1 up to about 0.4505 at 200 Hertz. And again, the circles are measurements, and in black we have the predictions of our model. This model has also been applied to aerogels, here with a similar degree of agreement. And here we have also now applied to describe the properties of zeolites, and we also doing a good job. So let's go into resonators now. So this is multi-scale porous materials, and now we are going to an array of resonators. So we consider an array of chemicals resonators, and we follow the work by Claude Boutin. And we have scale separation, and the sound energy dissipation is due to inner resonance and viscothermal dissipation. So we couple the Fourier-Stokes system with considering boundary conditions of this type, where VR is the velocity in the resonator here in the next. And so we will consider this resonator, we will model it as an effective, with an effective admittance, as we can see here. Instead of formulating the same system outside this resonator and inside and in the next. So we will just consider that this whole resonator is the behavior is determined by its effective admittance. So applying homogenization, we get the macroscopic description. Again, it follows the same type of structure, where the dynamic viscous permeability is determined by what's happening around this resonator. And effective compressibility has two components, one of them coming from the pore, so around this resonator, and another one coming from the resonator itself, where CR is an apparent compressibility which depends on the effective admittance of this resonator. So in black, we have the compressibility, the real part of the normalized compressibility of this array of resonators, chemical resonators. And in blue is the compressibility of, let's say, around what's happening around this resonator or the pores, which follows a classical trend. And in red, we have the compressibility coming from the resonator itself. So the black curve is a combination of the blue and the red one, as shown by this expression here. That's in terms of the real part. In terms of the imaginary part, here we have the classical picture, and in this case related to heat transfer in the pore. And at the resonant frequency, we have a sharp increase of the imaginary part that will lead to sound energy dissipation. So that's just the compressibility of this array. So we have some interesting behavior around the resonance frequency of the resonators. And now the idea is to combine these two type of media. So we have an array of resonators, and within the representative elementary volume, we have inclusions of nanoporous or multiscale nanoporous materials. So the idea was to get the best of both worlds, the best of the worlds of metamaterials, where we can exploit resonances, and the best of the multiscale sorptive materials, where we have very strong sound energy dissipation at low frequencies. So we will apply homogenization to this problem. and the sound energy dissipation will be due to inner resonances, viscothermal dissipation, classical dissipation, and viscothermal dissipation at different scales, pressure diffusion, mass diffusion, etc. So if we consider high permeability contrast between the pore space, so here in omega F, and the inclusion of multiscale porous material, then we will have that the permeability of the medium is determined by the permeability of the pores. And the compressibility will have a contribution coming from the pores, coming from the multiscale porous materials, and this apparent compressibility that comes from the resonators. So for the case of low permeability contrast, we have that now the permeability will have a contribution coming from the pore space and the permeability of the multiscale porous material with two tensors that are geometric and can be calculated from the solutions of conduction problems. And then the difference for the compressibility is that now Fp, so this pressure diffusion function will become 1, and the rest is identical. So this is an example of a material. We have a mesoperforated granular sorptive matrix in red. We leave space here in white, so just an annular pore filled with air, so that we don't kill the resonance, because if we put this sorptive granular matrix, let's say, touching the entrance of this neck, we will possibly kill the resonance. So this little gap is very convenient. And in gray, we have the Helmholtz resonator. So this now is coming from the top towards the bottom. This is a normalized compressibility. In gray, we have the sorptive material, so kind of like very smooth and continuous and with a large value. And in black, we have compressibility of the multiscale sorptive metamaterial with this discontinuity due to the resonance of the Helmholtz resonators. In practical terms, what we could get is that instead of having this sum absorption coefficient shown in gray, we can work and combine these two effects of resonators and sorptive material to get a much higher sum absorption coefficient, starting from about, let's say, 50 to 70 hertz up to 800 hertz. So in the circles are FEM simulations, and the black lines are the analytical models. So we have also applied the similar ideas, but for the case of membrane resonators. This has been recently published, and here in blue, we have a membrane resonator back with some activated carbons, and in red we have the same configuration, but instead of using activated carbon, we use a conventional foam. And in black, it is the empty cavity, so we have pretty much no absorption here, but some absorption can be greatly enhanced by the use of granular materials like activated carbons. So currently, what we are finishing now is our molecular to macroscopic modeling framework to model the acoustic properties of multiscale nanoporous materials. So previously, we have seen that we consider the propagation of sounds through the fluid part of the material, and we have assumed that the frame is perfectly rigid, and we didn't consider the propagation of elastic waves through this solid skeleton. But now the idea is to do both, to work out a way of calculating these mechanical properties of the materials, starting from the molecular scale, using molecular dynamic simulation, and also then upscale this system to account for acoustic and elastic wave propagation in multiscale nanoporous materials. So this is an example of two different types of zeolites. One of them is raw zeolite, and this is JST zeolite. We have considered a force field proposed in this paper, and these interactions described by Lennard-Jones potential. We consider interactions of silica and oxygen, OO, and SI. And we have harmonic functions describing the energy contribution from these different type of bounds and angles, but we didn't consider torsion because in this paper it is not considered, but eventually can be considered. We have published this first study on this in this journal, in the Journal of Physical Chemistry C. And in that particular paper, we have considered three different routes. One of them is what we call a statistical physics route. The three of them, the aim is to get the mechanical properties of this zeolite structure. And in the statistical physics route, what we do is to get molecular displacement and velocity field data by solving molecular dynamics models. And then we fit this data to a dynamic structure factor, SQ, and omega. Q is the wave number. And the second route is the mechanical route, which is from the simulations, we work out how this strain fluctuates. And from the fluctuation of the strain, we can work out the mechanical parameters following this classical method of Parinello and Raman. And the third route is the mechanical route too, but a mechanical test. The idea is to mimic what we normally do in, let's say, macroscopically when we test the mechanical properties of materials, like, for example, compression or extension test or shearing, excitation. But we do it with molecular dynamics simulation. That can be considered, let's say, like a numerical experiment. So the first route is we get this spectrum, and this is what we fit with this expression, which is, well, this is the way we calculate the dynamic structure factor from the molecular data. So J depends on the velocities that we can calculate from molecular dynamics. And on the other hand, we have that we consider the dynamic structure factor taking this form, which is essentially a mass spring damper system. So we calculate this from molecular dynamic simulations, and we feed this data using this model to get what? To get omega A, which are the eigenfrequencies, and from the eigenfrequencies we get the mechanical properties. And the second route is to get the C11, C12, and C44. These are the elastic parameters, and only these three because we have materials with cubic symmetry here. So with three elastic constants is sufficient to describe the whole elasticity tensor. And then, well, we have the evolution of the strains, the cross strains with on time. And when we get up to a certain convergence value, we can work out the value of E11, E11, and these multiplications. And with this formula, we can work out the compliance tensor, the S, and from the compliance tensor we get the elasticity tensor. And in particular, let's say H is the H matrix is instantaneous dimension. So when we do the simulation, we work out how this box will increase or decrease in size with respect to a reference system, and that allows to calculate these parameters. So that's the second route. And the third route is just, as I mentioned, mimicking the conventional mechanical test. So we, from the stress strain curves, we can linearly fit in this small strain regime to work out C11, C12, the elastic constants for both types of zeolites. So now that this table show the comparison of the longitudinal and transverse velocities obtained from the three different methods. They are pretty similar, all of them, just for rose zeolite and also for GST zeolite, for the two of the materials that we investigated. And once we have these, let's say, elastic parameters and densities, we can use these parameters as input for continuum-based models. So in particular, here we have a double porosity material. So this is a consolidated array of spheres that are nanoporous and elastic. And for simplicity, we started by considering empty pores, meaning that no fluid is filled and no fluid is filling the material. And we are therefore interested in only the elastic waves that propagate in this double porosity material. So we start with, sorry, the equation of conservation of momentum this constitutive law. We consider linear deformation and no normal stress on the surface of these nanoporoelastic spheres. And applying homogenization, we get that at the lowest order we have the displacement is a macroscopic variable, so it only supports rigid body motion. And then we get the corrector for the displacement by solving this linear problem that is forced by the strain, macroscopic strains. The solution is an operator, the third rank tensor acting on the macroscopic strain. So after that, we get the macroscopic description, which is a classical conservation of momentum equation, where in this case, sigma is the effective stress tensor, which depends on the macroscopic strain and the effective elasticity tensor. That takes this form, general form. This, in particular, this comes from the solution of this problem. And for a material with cubic symmetry, we know that we can write this elasticity tensor in this way, so we can match them and we can match them and get this elasticity constant related to the Lamé parameters, these first Lamé parameters and these shear moduli. So specifically, this is the relationship for the normalized first Lamé parameter and this normalized shear moduli, where F and G depends on the values that we can calculate from the solution of this local boundary value problem, this one. So in doing that, then we can work out the evolution of the, for example, the Young modulus or the Ink modulus, Book modulus, or Poisson ratio with the volume fraction of the solid. They all show an increasing trend with increasing volume fraction, which makes a lot of sense, obviously, because if we have, for example, 100% of solid, then obviously this first Lamé parameter will be the first Lamé parameter of the substrate. So we have to get this value of 1. There are interesting things happening in JST where, for example, we have auxiliary behavior for the substrate, but not for the double porosity material. So there is a critical volume fraction where this effect disappears. And rho is slightly different in terms of Poisson ratio behavior. Then with this information, we can work out, let's say, normalized longitudinal velocity, normalized transverse velocity, and in that way, we can link the molecular scale with the velocities that we can measure at the macroscopic scale in a lab. So what's the other thing now? If we include fluids, things become a little bit more difficult because we have to account for let's say effects of chemoelasticity. Chemoelasticity in the sense that we couple elasticity with diffusion. And we treat this in terms of chemical potential that has two contributions, one coming from, let's say, elasticity and the other one coming from concentration. We start with this system and we couple it with the Fourier-Stokes system in this pore, and this system here is formulated in this part. And when we do that and apply homogenization, we get this macroscopic description that looks like the Biot model. But the difference is that these parameters are exclusive to nanoporous media, and all of these parameters in red can be calculated from molecular simulations. And we've done that, and we are in the process of finishing off this thing. So we'll hopefully be able to discussing in more details all of these results in no time. So in terms of conclusions, well, we have investigated propagation of sound in multiscale metamaterials and presented a nano-to-macro modeling strategy. And what it is remarkable in this material is that many different physical processes are responsible for dissipation of sound energy. And also we have shown some of our progress on molecular to macroscopic modeling of multiscale nanoporous materials. So thank you for your attention, and I have to thank also our funders of these are, and I'm very happy to take questions. Thank you.
Thank you very much, Rodolfo. That was a very interesting talk, and I was interested to see that multiple scales have such a prominent effect. Let's see. Can I? Apologies, I need to find participants. Are there any questions? I can't see anyone raising their hand. Oh, there's someone raising. Keith Attenborough. Please, Keith, your question.
Yes, hello, an absolutely amazing talk. Thanks very much, Rodolfo. I've got a very simplistic question, really, compared with all the amazing stuff you shared with us. I'm thinking back to the very good sound absorption near 100 hertz you were able to get with your multiscale metamaterial, and I was just wondering what the thickness of that material was.
Oh, that's a significant thickness. It's 12.6 centimeters. This
Yes,
one
of
is to
course.
do with about 4 centimeters, let's say, per resonator.
Yes, well, you've heard me make this comment before, but as soon as you include resonators, then you have to have very much thicker layers, don't you? So you're not going to see this used on cars in the near future.
Possibly not. And we're hoping to get this thickness down to a more, let's say, acceptable level for those type of applications. And one way of doing that is by, for example, playing with this neck. So if instead of having, let's say a straight neck, we can make it tortuous so that the mass density is increased by a tortuosity effect, and that could reduce the resonance frequency, while at the same time diminishing the size of the cavity. So we have envisioned some ways of trying to reduce the size of these resonators so that we can have a similar effect with a much thinner layer. But I agree that even though these resonators are sub-wavelength, they are still sort of bulky, and we need to have space to have the cavities and all these elements of the resonator.
So
Another
one
way of doing this is to put, for example, activated carbon inside the cavity. So that also can reduce the resonance frequency, or we can make it smaller, but at the same time it would behave as if it had a larger cavity. So we can reduce the size of it by doing that too. So please, you were going to say something else, sorry.
Yes, sorry. Yes, I was going to say that maybe you've already thought of this by your making your necks tortuous, but of course you make the resonators tortuous too. So there's lots
That's
of
right,
work
yeah.
done up with coiled up space type resonators. So you could ally with that work.
Yeah, that's right. Yes, that's possible. The only the only comment I can make of this is that sometimes, yes, you can coil the resonance, but you make it much thinner, but then it becomes really wide. So it still needs space anyway. But the challenge is how to make let's say a better use of space by combining these ideas of metamaterials and this multiscale sorptive medium.
Thank you. Olga.
I have a question about the last part of your talk.
Yep.
About this molecular dynamics simulations. To calculate all these parameters for PO model using MDS, do you need to simplify the geometry, or can you do it for the realistic geometries, poor geometries?
For this,
No, the very
okay.
last one.
Oh, okay. Oh no, this one. I mean, yes, you can do it for basically any geometry. The only difference is that instead of having, let's say, only 3 parameters that use to describe the, let's say, the elasticity tensor, you will have more. So instead of, let's say, for example, in this particular case, we just need to excite, let's say, this force system with E11 equal to 1 and E12, and obviously E21 equal to 1. So we only need 2 simulations to solve this problem twice to get all the information we need. So for a material with a much more complicated but periodic geometry, we will have to just excite the system in E11, E12, E13, and so on. 6 different type of excitation, and then we can work out the entries of this elasticity tensor without any problem. So, so the answer is yes, it is possible to do it with some more complicated geometries, but it must be periodic. And the only difference is that we have to solve this problem 6 times instead of 2 in this particular case.
Does this mean that this problem of a huge amount of parameters in BO model is practically solved? You can numerically evaluate all these parameters for.
Yes, you can from the microstructure you can get them all. And another complication would be this, because for example, for a much more complicated material, without, let's say, one without cubic symmetry but rather fully anisotropic, then you have that the wave is not that easy to get the, let's say, the different velocities. You have to solve the Christoffel equation, and that makes it a little bit more difficult from a technical point of view. But it's not obviously not impossible to do it. It's just it's more, say, tedious. And
Extensive. Okay.
yeah, okay. Thank you.
Thank
Well,
you.
thank you very much. Any other questions? I don't see any raised hands or anything in the Q&A portal. If there is no questions, then thank you again, Rodolfo. That was a fascinating talk. Very interesting one. I'll intend to chase it up and I follow it up when I can. But just remains, thank you very much, and remind everyone that a recording of this webinar will be available in UKAN YouTube channel in due time. And that is it. Thank you so much. And I'm going to stop recording.
Thank you so much for this opportunity. It's been very nice.
Rodolfo.
Hope to see you all soon, very soon.